Kia ora koutou. This video is from the 2009 Scholarship Calculus paper, and it's the only question I remember seeing that uses Simpson's rule for what is, I think, a really nice algebra and easy integration question. So this question is fine as long as you know what Simpson's rule is and how it works. Otherwise, the chances that you get bogged down in the formula are not low. So I've just done a video going over the basics of Simpson's rule. So go watch that if you decided you would ignore this content for level 3 integration, which I reckon is a bad decision. But there you go. Okay, so this question says, show that Simpson's rule using n equals 2 gives an exact answer when integrating any quadratic here on this interval r is less than or equal to x is less than or equal to t. So when they're talking about n over 2 in here, I haven't snippy tooled the Simpson's rule formula in the formula sheet, but it will be something very similar to this. So s is approximately, it will be h over 3. I'm just trying to work out what notation they've used to write it down. I think it will be this, y0 plus yn plus 4, y1 plus y3 dot 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 plus yn minus 1 plus 2 times y2 dot 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 to yn minus 2. Now, if you're not kind of used to what is going on here, this can look a little bit daunting. But what this is saying is that we're going to have two intervals, and we have to figure out what this h thing is here. And we've got some quadratic with a, b, and c, as usual, over this interval. So I've done a little graph to show us what we're going to be doing. So this is just a generic quadratic, ax squared plus bx plus c. And we're trying to show that when we use Simpson's rule, that the area under the curve using the approximation, using Simpson's rule, comes out to be exactly the correct value when I integrate it. So we can just whack in some lines here, and these are going to be my limits of integration. So this is r and this is t, and we want to use n equals 2, which means we've just got 2. We really could rule those lines, couldn't we? Make it like a proper maths video. There you go. Okay. Apologies to any maths teachers watching for the crap graph. Right, 2 intervals means that I'm just going to put a line in the middle here, and that line in the middle is going to be at the halfway mark of those two things. So that's going to be at r plus t over 2. As usual, a good graph has got us just about halfway through this question already. Right, so let's take a look at what the two things to do here are. Well, if we're going to show that it gives an exact answer, we might as well go ahead and get the exact answer and then do the approximation. The reason I'm doing it that way is because we're going to have quite a mess coming out of Simpson's rule, and then we're going to try and match it up to where we're going on the exact answer. Okay, so the exact area is going to be the integral from t, we'll just change pen colour, so from t to r of ax squared plus bx plus c, integrated with respect to x. Very easy level 2 integral. It's just a over 3 x cubed plus b over 2 x squared plus cx, and then we're evaluating at these limits. So substituting all of that in, I get a over 3 t cubed I get that minus everything evaluated at r and I'm going to do a little bit of cleaning up on this first so that I have a good thing to be looking at when I'm doing the Simpson's rule part of the question. Right, so I get a over 3 t cubed minus r cubed plus b over 2 t squared minus r squared plus c times t minus r. Okay, so that's my exact area. And now we're going to have a look at what's happening with Simpson's rule. So going back to this graph, what I need to do here is to make the rule work. Oh, the rule's disappeared. That's kind of weird. Where's it gone? So S is equal to h over 3 times y0 plus yn plus 4 times the odd numbered values plus 2 times any even number values. Right? These are my endpoints. So in this case, it's a really simple example because I've got this is going to be my y0, this y value here. This is going to be my y2, and I've only got one other one to do. And so that's my y1, and that's going to get times by 4, right? I don't have any of this because it's a really nice question with just 2 intervals, so we can forget about all of that. And that means the first thing to do is to figure out what is the height of that function at each of those places. So let's do that off to the side first. So y0 is f of r, y2 is f of t, and the messy one is the halfway one. So y1 is f of t plus r over 2. The width of the intervals is going to be the total distance divided into how many we've got. So h is going to be t minus r divided by 2. F of r is equal to ar squared plus br plus c. F of t is equal to at squared plus bt plus c. And then f of the average is going to be equal to a times r plus t over 2 squared plus b times r plus t over 2 plus c. Now I'm not going to expand all of that out because hopefully some stuff is going to fall away. Now that we've got those, we're ready to put that into the big expression for Simpson's rule, which is 1/3 times the width, h, right, which is t minus r over 2, times the endpoints each in once. And you can see straight away, if I add those together, because it's a scholarship video, I'm going to go straight to doing this. Now the reason I'm grouping here is because I've already done that exact integral, so I know that I want to be ending up with this kind of pattern where I've got the a stuff here, the b stuff here, and the c stuff here. So I'm starting to do that with this. And now I have to add in 4 times this value. So it's going to be 4 times a times r plus t over 2 squared plus b r plus t over 2 plus c. This here cleans up to t minus r over 6. We'll write this out again. And now here, the 4 and the 2 squared go away. And I'm going to have a times r plus t squared plus the 4 over the 2 gives me 2 b r plus t plus 4c. Right, now keep on going. We're just going to group everything into the a's, the b's, and the c's. So in here, we've got a times r squared plus t squared. Finally, we're going to expand this. So we get r squared plus t squared plus 2rt plus b r plus t, and 2 lots of b r plus t gives me 3b r plus t. And I get, something's gone wrong here. Why have I got 5c? What have I done? I've done something silly here. Hang on. I should have 2c back here. Oh, yeah, I've missed a 2c. Look. Okay, this is why we check, right? I've got a plus c here, and I've got a plus c here. So this should be plus 2c in here. We'll just go back and fix that. So 2c and 4c is now giving me 6c when I clean that up. And you should be getting a feel that a whole lot of stuff is about to match up to that exact one. So here we've got t minus r, so a times t minus r on 6. And we've got what coming in here? 2 lots of r squared plus t squared plus rt. Here we've got 3b times t minus r, t plus r over 6 plus 6c t minus r over 6. Right, so we've got a over 3 times t minus r, t squared plus tr plus r squared plus b over 2 times difference of 2 squares, t squared minus r squared plus c times t minus r. So let's go back to the start, to that exact value, and see how we're going. Well, we're really happy we've got that matching and that matching. And if you remember back to session 1 of Scholarship Calculus this year, if you're coming to Dub C or Saturday classes, this expression for the difference of two cubes fits exactly with what we've got down here. Now, if you had forgotten the difference of two cubes, you're going to waste a couple of minutes doing that expansion. But we don't have to, right? So we've got t cubed minus r cubed here, plus that. Now, I haven't marked Scholarship Calc. I think it's fine to go from here to here. I think it's a standard enough result. I don't know how you show the marker that you actually know that, instead of going, hey, I'm nearly there, I'm just going to write the answer in. Maybe you do have to expand that out. I don't know. Someone watching can tell me. If there's someone here who's marked Scholarship Calculus, please let me know. But here we get t cubed minus t squared r. I'm sure you don't have to do this. Plus t squared r minus tr squared plus tr squared minus r cubed, which is t cubed minus r cubed. So that was just a bit of revision for you of like the proof of why that works. Okay, I think this is a really, really nice question. I was pretty surprised how hard people found it, but I think that is just because Simpson's rule, if it's unfamiliar, is going to kind of stop you in your tracks on this one. It shouldn't. Simpson's rule is a really, really easy and useful approximation. If you're doing level 3 tomorrow, just make sure you've gone over both that and the trapezium rule in case there's a question that does mix up easy and hard bits of it. Thanks for watching. I'll be back with some more videos later on today.